Thank you, Amelia, for your introduction. I'm glad to take this opportunity today. My name is Timo Uldak. I'm working as a technical marketing manager for Magic Power Modules for Würth Elektronik since now October 2014-15. Today, I will talk about PCB layouts, tips and tricks, EMI, and thermal obstacles in the field of micromodules. First, let us talk about some fairy tales around PCB layout. Everybody was talking about PCB layout says, oh, you need over 100 years of experience and you have to use expensive software tools and you need a lot of prototyping layouts to test it. To be honest, I'm doing this now over nearly 20 years in this power electronics business. That's completely wrong. These are all fairy tales, believe me. The truth is that PCB layout is not a rocket science. It's just bringing your schematic to the real life. But how can you realize this? With the right setup of tools, and I'm talking about tools, not about software, and a little help of Ohm's law, it's just easy as riding a bicycle, believe me. So what we talk about is the micromodules, the applications, to get a basic start point. We're talking about the basic layout considerations. We're talking about the EMI compliance, the thermal management, and the production requirements for a good layout. Let's get on. First, to have a common understanding about the setup of a real application, let us check the following example where we use a micromodule. The application consists of an energy source, like a battery or USB marked in black, a DC-DC converter that's in red, an image sensor, an MCU unit, and Wi-Fi communication devices. The DC-DC converter here regulates the 5 volts that comes from the battery or the USB port down to 3.3 volts, providing a stable regulated power to the MCU. The MCU then processes the data, initiates follow-up actions, and sends commands to the sensors and the Wi-Fi module. The RF module then sends the data from the image sensor via Wi-Fi to the master receiver unit. From there, the data will be processed and visualized, perhaps on a display. So now the design calculations are made and schematic is completed, what we see on the left. But how can we properly lay out the application with the micromodule and its peripheral components? As always, there's not only one path that leads to the goal. Here we have two possible ways. The simple way, and let's call it the sustainable way. Both have their advantages and their disadvantages. The easiest method would be to download the general purpose layout from our online catalog, allowing you to copy and paste the micromodule with its peripherals components into your existing design and quickly integrate the power module into the application. The general purpose layout has acceptable EMI and thermal performance, while maintaining manufacturability according to most EMS design guidelines we tested. The evaluation boards of the power modules are realized with this type of layout. The general purpose layout is, we call it, a good starting point. While a general purpose layout is good, how can you tailor a layout to provide the best performance for a specific application? And the answer is always as easy as it is. It is like changing the car's tires. With the right tooling, everything's fine. You only need to add here 3 new tools to your existing layout toolbox you already have. First, EMI compliance. Second, thermal management. And third, production requirements. To better understand the tools, we shall first discuss a few basic concepts. Let's start with the EMI compliance. Every line we place using a layout tool, such as Altium, corresponds to a real element in the physical layout that has parasitic characteristics that are undesired for the application. A conductor, such as a trace that forms a loop, creates an antenna. This emits a field when AC current passes through the trace. Let's now take a closer look to the loop aspect and its effects, because they are very important for any radiated emission. The correlation for the field strength can be expressed by the shown equation. It's heavily depending on the frequency, the amplitude of the AC current, the overall loop size, and last but not least, the distance between the noise source and the noise sink. To get here a little bit more numbers, I made an example. The example shows that the loop area with the size of 1 euro-cent coin creates nearly 3 times more dB microvolt per meter than the limit values of the CISPR 32. But a direct correlation to the measured value of a radiated EMI in the lab is not possible, but this should visualize the orders of magnitude. Using this analyze technique, we can now look at the switching behavior of the micromodule in our application in a different light. The micromodule we have designed in this application is a power module with a synchronous buck topology. The block diagram visualizes the current loops during on and off state. These loops represent the critical EMI path for radiated emissions. The green loop is during the on time of the converter. This is loop 1. And the red loop is during the off time of the module. This is the loop 2. Both, as already mentioned, are the sources of radiated emission. One, the loop that is created by C in over V in over V out, C out and back is the source of radiated emission. Then, second, the feedback pin. This is where you measure the output voltage and adjust the output voltage, is highly sensitive in terms of any noise that is fed in here. The noise can affect the value of the regulated output voltage. Third, the enable pin is sensitive in terms of any noise that is fed in here, because with this pin you can enable or shut down the power module. So any noise that comes in here could shut down unintentionally the power module. Fourth, the power good pin can be considered non-critical from an EMI perspective, because this pin only gives you a signal that the power module is on or not. Fifth and last, the power ground can also be considered as non-critical from an EMI perspective, because this is the ground and any noise that is fed in here is not going to harm the device. Now, to get a little bit more understanding about loops, let's modify the Micromodules recommended layout by moving the input capacitor on the left, Cin, only 3 centimeters away from the Micromodules pins. What you see here is that 3 centimeters results in multiple exceedances of the limit values of the CISPA 32. The emission exceeds the compliant limits dramatically. The design here would fail the EMI measurement. And now, let's get back to the optimum. Let's return the input capacitor to its recommended position, as close to the input and ground pins as possible. The effective loop is now minimized to its absolute minimum value. What you can see is we have here over 10 dBs margin. The effects we analyzed can now be summarized to the C-in position affects the current loop area. Bigger loop results in more radiated emissions. Higher field strength results in more disturbances that can affect the application. This is very, very interesting, and please note this down. The next slide will show the do's and don'ts for a PCB layout, EMI-wise. How do I distribute the ground reference through my PCB? The first option we're going to see here is obviously wrong. When you connect any point in your system with more than one path of ground, you may create a ground loop. Any disturbance that is coupled into the loop will drive current. This noise can affect the whole system. Especially when you have long cables connecting different devices, this might turn into a radiated emission problem. We want to have as little as possible of this shared impedances in this ground and VCC lines. That's why we usually distribute ground in a star topology, what you can see here. This not only helps with emission, but it also is good for immunity. A ground plane should not be interrupted, if possible. At AC and DC lower frequencies, on the left, the return current flows back the paths of least resistance. At higher frequencies, the return current flows along the path of the smallest impedance and thus directly under the outward current conductor. That's the picture in the middle. If there's no flat ground system, or if it's very fragmented, like the picture on the right, the high frequency return current must take a diversion that inevitably ends in a surge point due to the false impedance. Using the example of a digital IC, the basics of C-in positioning can be explained. The basics here are the same as for a switching regulator IC or a power module. The picture on the left shows a design with a large current loop. The design in the middle is an improved version of the left one. The overall area of the loop is reduced by routing the ground under the IC and not around the outside of the IC. If we now enlarge the ground trace under the IC to a field that is shown on the right, we get to design, which is here the optimum, which is the best. Let us start with the picture on the left. The left picture shows a design where the via has been placed between C-in and the VCC pin. This configuration is not optimal because VCC is able to receive current through the via without being fully decoupled by C-in. So this is a bad design. Traces that are routed in parallel and have different potentials can interfere with each other. Interferences on the VCC trace can couple in an I/O trace, which is shown in the middle picture. The design on the right illustrates the loops theme. Both ICs are connected with a long VCC trace. An optimum design for placing C-in is shown on this slide. High-frequency transient currents into the IC are supplied directly from the capacitor. The via is on the right of the capacitor, so that all the current from VCC is supplied by the capacitor. Be aware to connect the capacitor as low impedance and balanced as possible. In case of a 4-layer PCB, VCC and ground are additionally supplied by the capacitor of the planes. C-in placement here is valid for a connection of a VCC pin that has to be decoupled, like for a power module, a digital IC, and so on. So far, we have only talked about the noise transmitters. But what about the noise receivers? How are the interferences mechanism designed here? First of all, loops are loops. That means they can both transmit and receive. The basics we have discussed so far generally apply to receiving also. A large loop area can therefore catch a lot of interference, and small areas accordingly less. The circuits mark the loops through which interference can be coupled to the respective pins. The capacitors C-in and CFF must be placed very close to the enable and the feedback pin, so that no disturbance can be catched up here. Every conversion from a higher voltage to a lower voltage is not perfect. This is physics. There is no efficiency of 100%, so we will always have losses on the PCB. The next couple of slides, I will talk about PCB layout regarding thermal aspects. There are three basic mechanisms of heat flow which need to be considered. First of all, there is an internal heat conduction in the material, leading the heat to the surface of the PCB. From the surface, heat is emitted to the ambient, either by heat radiation or convection. Main difference between these two lies in the way they interact with the environment. While convection heats up the ambient, heat radiation will heat up the surrounding object. As you can see, the calculation becomes here very complex. as the calculation has to be done not only in X and Y direction, but also in Z direction. To save time here for you, we have a new Red Expert tool for our SMD buck converters power modules that helps you a lot. You can see here the 3 boxes for the thermal behavior panel. The box on the left side shows the power loss of the magic power module at a certain operation point, scaled over the output current of the module. The middle box shows the simulated case top temperature versus the board area. And the last box on the right contains a heat map of our evaluation board with all components placed showing the heat distribution at any point of the PCB. Now, last but not least, the producibility of the layout is no less important. What helps the best layout if no AMS can manufacture it? An important aspect here are the thermal wires and their placement. The design here shows the first approach, how the wires can be placed. The wires are placed on the side of the exposed pad. 2 rows here with 5 vias each. The diameter is 200 micrometers, and this is a standard value offered by every PCB manufacturer. The second approach, the vias are placed directly in the exposed pad. 3 rows with 3 vias each. Both approaches can be found in real applications. But now the big question. But where is the big difference from a manufacturing point of view, and when should which approach be chosen? Normally, if this would be a live session, now a lot of fingers would raise and we couldn't get into a discussion. So I will now give you the solution. The first approach is very easy to manufacture because the vias don't need a special process. The second approach is more difficult because the vias have to be filled and capped to prevent solder wicking between layers, so that the solder is not going to flow from the top layer to the bottom layer unintentionally. But due to the direct connection from the heat source through the vias to the bottom layer, the thermal performance is better. So the first approach is easy to manufacture. The second approach needs a more, let's say, educated or more specialized EMS, but in terms of heat conduction, it is better. So I hope everything is fine. You could understand me, and if you have some questions, I will stay in the line. Thank you, Amelia, and yeah, thank you. So I get some questions here on the chat. One question is, what can I do if I'm not sure if my self-designed layout with a power module is sufficient? Oh, this is very, very easy to answer. If you need any help in terms of layout or in terms of design in or in terms of EMC filter design, please we have got a hotline. You can type in power modules at we-online.com. First comes, first get. Everybody who sends us an inquiry about a question about this technical stuff will get an answer immediately. Normally, we're talking about 24 to 48 hours response time, because we know that design questions are very, very time critical. Let's check if there are more questions. Okay. Is there a thermal difference with 9 or 10 vias? Very good question. That depends a little bit on the diameter of the holes you have and the placement here, but roughly you can say that there is a difference, but it is not, let's say, it is not so critical. Something about the starting layout. Are the layout files free of charge? Of course they are free. So if you want to have a layout data from our power module, or if you want to have it from the evaluation boards, go online to our online catalog, download it. If there's something missing, or if there is something you need special, please contact us. We will try to help, because we only have Altium, we have got Cadence, and we have got, sometimes we have also, what is it called? I forget the name. This is this free of charge tool. We have it also. So we have got multiple formats of the layout. And as I told you, if there's any special, please call us. So are there any more questions? Wait, no. So Emilia, there are no more questions. I think I have to thank you for hosting this, also DigiKey, that they gave us the opportunity here. And yeah, I will get back to Emilia. Thank you.
Thank you very much, Timur, for presenting, and thank you everyone for joining us for today's Wurth Electronic webinar. As a reminder, if your question did not get answered today, or if you think of them a little bit later, simply email us at hereforyou@we-online.com. And remember, register for our next webinars. They will be coming up in April. First, we're going to take a look at Introduction to Inductors on April 7th. And also in April, we have our first power webinar of the year. This is a joint presentation between Wurth Electronic, Matrix Industries, and Renesas. We'll be presenting energy harvesting, now a real and efficient solution, on April 13th. Register online at www.we-online.com. Thank you for joining us for today's Wurth Electronic webinar.